Good evening, friends. Today we are going to talk about electromagnetic induction and AC generator. First, let's see what is EMI. Electromagnetic induction is a process by which a changing magnetic field linked to a conductor induces a current in the conductor. In the previous section, we have seen it that when a current carrying conductor is placed in a magnetic field, it experiences a force. It means with the help of the current and magnetic field, we are producing force. So if now, by changing magnetic field, if a conductor is placed in changing magnetic field, then this induces current. This is known as electromagnetic induction. Now, this principle is used for the power generations in all the AC generators, and wherever we have the requirement of power, the electromagnetic induction is used over there. This phenomena was coined by the Michael Faraday. That's why this is also known as Michael Faraday's electromagnetic induction. Now, necessary condition over here is that field must be variable. If it is not changing, then there is no current induced. If the field is changing, then we can say the current is inducing. Now, let's take one experiment which was done by Faraday. What we are doing is taking a wire, a bar magnet, and a galvanometer. We need a bar magnet to produce magnetic field, a wire, or a conductor to set up the entire this experimental setup. Now we have to do is move the magnet towards the coil. This wire acts as a conductor, magnet is to set up the magnetic field, and galvanometer to check the direction of current and to measure the current. Now whenever we are moving the coil towards the wire, whenever we are moving the magnet towards the wire, what is happening is we observe there is a deflection in the galvanometer. Be it right or left, any side, we don't know it, but there is a deflection in this galvanometer when we are moving it. As soon as we stop the magnet, in the case the magnetic field stops changing, it remains constant and the current becomes zero. Again, what we are doing is taking the magnet away from the coil. If you are taking magnet away from the coil, it means the direction of magnetic field is changed now. So it induces the current but in the opposite direction. So that's why galvanometer shows deflection but in opposite direction, which indicates that current is flowing in opposite directions. So now conclusion over here is a moving magnet towards a coil induces a current in the coil, because if you are moving a magnet towards a coil, it means you are changing the magnetic field which is linked with that coil. We can take this as an analogy, like you're pouring the water into a glass. If you're pouring, it means the water level is changing. As soon as you stop pouring water, its level becomes constant, fixed. The same happens over here. When a magnet is moved towards the coil, its magnetic field changes. Initially, there was no magnetic field linked to the coil, but as magnet is coming towards the coil, it means it's experiencing a magnet. It means it is changing. Once you stop the magnet, it means the changing magnetic field becomes zero. Again, you start moving this magnet, it means the magnetic field is changing. That's why the changing magnetic field produces current over here. We have one more here you can see this. As soon as the bar magnet is moving towards or away, the magnetic field is changing, and here we can see the current. Now here the important point is the speed with which the magnetic field changes. It affects the amount of current we are getting. If you are moving the coil very faster, or if you are moving the magnet very much faster, it means the magnetic field is changing much faster, and magnetic field is getting slowed down much faster. It means change is very fast. It is increasing very fastly, decreasing fastly. It means changing very fastly. Then this rate of change of magnetic field affects the amount of current induced. Now let's take one more example, one more experiment in which instead of using a magnet, we are using electromagnet. How? That we are inducing the current in a coil. So here you can see the first circuit. We are inducing the current. As soon as you close the switch, we have studies that current is passed through a conductor, magnetic field is set up. So as soon as you close the switch, magnetic field is induced in the first coil. This magnetic field will create some force in the second coil. The second coil have the changing magnetic field. So first, as soon as we close the switch, there is a magnetic field induced in the coil 1. This magnetic field now interact with the coil of the second circuit. Now this secondary coil, since there is a changing magnetic field, it shows deflection. But what will happen after 1 second, 2 seconds, after some time, the current becomes constant. It means magnetic field becomes constant. If the magnetic field is constant over here, it means the magnetic field which is linked to the secondary coil also constant. So if the magnetic field is constant, I mean after some time there is no deflection in the coil. Now, what will happen if we replace this battery with alternating power source? If we replace this direct current with alternating currents, we know that alternating current, the magnitude increases and decreases, it doesn't remain constant. So in alternating current, the magnitude varies. If magnitude of current is varying, it means the magnitude of your magnetic field also changes. If current is changing, it means magnetic field is also changing continuously. And if magnetic field is changing, which is linked to the coil 1, it also changes with coil 2. So if there is a change in the magnetic field, so we get the current, or we get this deflection in the galvanometer. Now this principle is used in electric generators. Now what are the electric generators? We have seen it in commercial buildings, or in the top of the residential building, apartments. Even during the marriages there is a diesel generator. So what it does, it provides electricity. How they are producing, they are giving input as in diesel, and they are getting electricity as an output. So any device which converts mechanical energy into electrical energy is called electric generator. Mechanical energy is getting converted into electrical energy. Now whenever we talk about any appliance, we always talk about the 4 principles, which 4 points. Out of the first one is, what is the principle? Second, what is the construction and diagram? Third, what is its working, and what are the applications? So a principle we have already seen. Principle is the electromagnetic. Induction, it means when a current conductor is linked with variable magnetic field, then current gets induced in the conductor. So here what we have to do is, inside a generator, the conductor keeps on rotating in a magnetic field with the help of external circuits. So if the conductor is rotating, it means it will induce current. It will produce current. Now here is the basic circuit diagram. It is pretty much similar to that of your motor, but only difference is, in motor we give electricity and get mechanical energy as an output. Now here the mechanical energy is given, but the output is your electrical energy. Now let's see this construction. First of all, we need a conductor. So here is the armature coil A, B, C, D. This act as a conductor over here. This is a rectangular coil of insulated copper wire. Insulation is done in order to prevent short circuit. Now we need the magnetic field, so we have magnetic poles, one north and one south pole, to set up the magnetic field. Now 2 rings. Here you can see the end of this coil is connected to the 2 circular rings, R1 and R2. It is complete circular rings over here, and it act as a here adjuster. It transfers the current from the armature to the external circuits. Now its AC generators, slip rings are used. We have slip rings over here. This slip rings, sorry, this is split rings, just misplaced, just change this word. The slip rings here are placed on the axle, which can rotate freely. Now the rings is where we have to see split, where we have to use slip rings, where we have to use split rings, which we'll see in the upcoming upcoming video. And then we have brushes. We have 2 brushes, R1 and R2. R are 2 rings, and B1 and B2 are 2 brushes. So B1 is connected with R1 and B2 is connected with R2. So what the B1 over here is, it is just touching. If this is your ring, it is just touching, the brush is just touching it. There is no like proper connection or welding or joint. So what it does is, one thing keeps on rotating and another thing keeps on touching it. So brushes are made up of carbons. Why? Now the brushes are made up of carbon because carbon is a very good lubricant. So it reduces the friction and it reduces the wear and tear. And then last we have the galvanometers. It means this indicates like there is a current, and it also tells about the direction of current. So that's why we use galvanometer over here. Now how the working takes place. A coil is placed inside a magnetic field. Now we have to rotate it. So let's say we are rotating it in this direction. So AB is moving upwards and CD is going downwards. So what will happen, we'll apply its right hand rule over here. Fleming's right hand rule. The directions of magnetic field is represented by the first finger. So this one is the direction. Now we are rotating AB upwards. So this is the force. The force is going upwards and this is going thiswards. So this fingers, the second finger, represents the direction of current. So current will induce in AB in this side. And if you just change, the force in this one is downward direction and magnetic field is still from north to south pole, then the current is towards you. So in the one part, the current is going away from you. In the second segment, CD, the current is coming towards you. So this is making a complete cycle. Now what will happen if you're rotating some devices, after half rotation, the AB will come at the place of CD and CD will come at the place of AD. It's just like a turning the book. If you're taking and this turning. So this fingers and this thumb, these two replaces each other if you turn like this. So what will happen, the property which was shown by AB side, now it will be shown by CD side. So direction of current in DC will be from D to C, and from B to A, it will be from B to A. So in this segment, it was from A to B and C to D. Now it is from D to C and A to B, the current is reversed. Now this current is linked with these two rings. So these are connected with the rings. So they are transferred to the rings. Now from the rings, these two brushes are connected. So they transfer this current to the external circuit. So current is getting reversed over here from A to B, C to D, but after half rotation, D to C, B to A. It's just the opposite directions. We can find direction at any point of time by applying Fleming's right hand rule. We just have to carefully align the first finger in the directions of magnetic field, second finger will show your current, and the thumb will show your force. Here you can see how a generator coil rotates. The one end of your coil is always connected to the one ring and the second end is always connected to the another ring. It's just like they are touching it and they are rotating. So here you can see the armature is rotating in one direction, but continuously we are getting the current in two directions, from left to right and then right to left. This galvanometer deflection shows which side current is flowing. Now, how we are rotating this armature coil? So, in power generation, what we do, whether it's a wind energy or a hydro energy, let's take about the hydro energy example. You can see in this GIF format. Using the hydro energy, the wheel is rotated, turbine is rotated. Now, this wheel is connected to the shaft of this armature coil. We have a shaft over here which is connected to this wheel. So what will happen, if this wheel is rotating, then shaft rotates. If the shaft is rotating, all the things which are connected to the shaft, your armature coil, the rings, these starts rotating. And once these starts rotating, it means they are in a changing magnetic field. Magnetic field will change with this. So magnetic field is changing, it means we are getting the current. Now here I have written the working of how the AC generator works. You just you can go through it. And then we will talk about where we have to use split rings and where we have to use split rings. See, the split ring concept is used with the concept of DC current. And if the current is AC, then we use the slip rings. So slip rings means AC current and the split rings is DC current. So whether it's a AC generator or a DC generator, AC motor or a DC motor, if it is AC motor, then we are using the slip rings. If it is DC motor, we are using the split rings. The split rings are disjointed rings and the slip rings are complete rings. The split rings changes the direction of current. So in slip rings, let's talk about first. In slip rings, the current is getting reversed alternatively. If we get once this side, then after half cycle we are getting in this side. So what does a split ring do? It changes the second direction to the original direction. It's changing the direction of your current to the original direction. Those split rings helps in the maintaining DC current. That is the use over here. Now the applications, we have seen this. All the power generating stations except solar generator is used. So this phenomena of electromagnetic induction is used. In our homes, in the commercial building, we have seen the diesel generators. Even in the diesel or electric motor locomotives like train engine, this concept is used. Then we have transformers. Well, not this one. Transformer is device. You might have seen this outside your street, somewhere near your colony. So what these do? They changes basically the voltage level of electricity for transmission and distribution purpose. Now, when power is generated, it is generated approximately at 220 to 240 voltages. But if we transfer the power at 220 voltage, the losses will be very high. So we have to increase its level, and again for our home purpose, we have to decrease the level. That's where the transformer roles takes place. Now it works on the principle of mutual induction. It's same like electromagnetic induction. Now we have two type of transformer. One is called step up transformer and another one is called step down transformer. So step up transformer means step up, yani we have to increase the level. So step up transformer increases the level of voltage output, and the step down transformer that reduces the output voltage. So with this, we have completed AC generators, electromagnetic inductions. Thank you very much. Be with us, and if there is any doubt, you can drop your comments. Thank you.